Thank you. So I'm going to speak on my joint work with Mark Shusterman, which is a few years old. And so what I'm going to do in this talk is give a new perspective on it based on things I've been thinking about recently and kind of make some speculation. And so that's everything is right with Mark Shusterman, except any errors in the speculation you should blame only me for. So I want to tell begins with Chowla's conjecture, which involves the Möbius function, which is Möbius of n is minus 1 to the r if n is the product of p1 through pr, prime and distinct, and 0. Otherwise, in other words, if n has a repeated prime factor. And the conjecture is that if we sum for d1 or dk integers, we sum for n less than x, Möbius of n plus d1 times up to Möbius of n plus dk. It should be little of x, as long as d1 through dk are distinct, or even sum d appears an odd number of times. So this is a very hard conjecture. There was not very much progress made on it in a long time until this breakthrough work of Möbius and Additive. And then further work building on the breakthrough by those two authors, and Tao and Tervainen. I've got Zhao and Ziegler. Maybe someone's name I forgot. But during the time when there wasn't that much progress on it, Sarnak came up with Sarnak's conjecture, which was designed to be a stepping stone to Chowla's conjecture, a statement which follows from Chowla's conjecture, but is much more approachable. Which has to do with the concept of a zero-entropy sequence. So F, and from the natural numbers to complex numbers, zero entropy if it is bounded, and for each epsilon and k, there are e to the little o of k tuples such that f of n plus 1 up to f of nk is within epsilon of 1 k tuple on the list for all f. So if you look at subsequences of length k, you don't get all possible subsequences of length k. You get only a small subset of that. And the conjecture of Sarnak is that sum for n less than x, half of n, of x, for f deterministic. Theorem Chowla, conjecture, imply Sarnak. And the argument is quite straightforward. You show this. Sum has to cancel on most subsequences of length k by choosing each of these possible things and like hitting it with your sequence and like taking some power and relating it to this. That was a very good question. So by kind of elementary argument, we got this implication, and there's a logarithmically average converse. So what I want to talk about today is the analog with polynomials over finite fields. So many different statements in number theory have analogs where we replace the integers appearing in a statement with polynomials or finite fields, and we can study those. We can give multiple possible justifications for doing this. Well, in the spirit of this workshop in a special year, I'll say that a very good reason to do this is it gives the potential for deeper connections to algebra and geometry and algebraic geometry. And so to do that, we need to set up a dictionary. We think of an integer as corresponding to the ring of polynomials in one variable over a finite field. Fq, with Q is equal to P to the R elements for P prime. Probably don't need to say that in this talk. And we're going to think of the natural numbers as thinking of and corresponding to a set of monic polynomials, which I'll write FQ joined T plus, monic meaning the leading coefficient 1. And we're going to think of primes as corresponding to monic irreducible polynomials. Monic is not 1, and you can't factor it into two polynomials, which are monic and not 1. And so the Möbius function in this setting is defined the same way. Möbius of f is minus 1 to the r, if f is equal to a product of pi 1, pi r, pi I prime. Distinct and 0 otherwise. So the conjecture on or the FQHT analog of Chowla. Is that for D1, so DR and FQHT, the sum over F monic polynomials, degree F equal to N, Möbius of F plus D1 times Möbius of F plus DR should equal to little o of the length of the sum, which is Q to the N, or as long as D1 through DR. All right, let me make this K. D1 through DR.
N going to infinity of Q, but
Q is going to be fixed in this talk. So N is going to. So D1 through DK distinct, or more generally, if one occurs at odd number of times. So the theorem, myself and Mark Shusterman, is the conjecture is true if Q is greater than K squared times P squared times E squared. So K is the number of terms in the product. P is the characteristic of a finite field, and E is 2.718. You didn't miss a parameter E somewhere. And so this is a kind of funny statement. So most of the time, when we think of finite fields, we think of the simplest examples of finite fields are prime fields, where Q is equal to P. So this theorem proves nothing about prime fields. It proves nothing about prime square fields, but it does apply for all other finite fields with only finitely many exceptions for each K. And if you let Q grow in powers of a fixed prime P, the number of K which you can handle by this group grows quite rapidly with Q. It grows exponentially with Q. And then another thing I want to point out with the statement, this is a weak form of what we proved. I mean, this conjecture, as I wrote it, is a very weak statement because I only have a little O here. I have no effective bound of the conjecture, and there's no uniformity in the shifts. And so the actual statement that we proved gives, I think kind of a lot of the strength things you would hope for. It gives power savings. Oh, like you get O of Q to the N times 1 minus delta. With uniformity in D1 through DK. And you can get the result in short intervals or arithmetic progressions. And then all depending on Q. So the larger Q gets, the more power savings you can get, or the more uniformity you can get if you want like really enormous shifts, like bigger than N. You can do that, but at the cost of some power savings. And you can go to short intervals. The shorter the interval, the less power savings. But as Q grows larger, you can buy the power savings back. So after proving any form of Chowla's conjecture, there's at least two natural things to try to do. So one is to prove results about primes by using Chowla's conjecture to resolve the parity problem in results where the parity, in conjecture where the parity problem was the main obstacle. And another thing is to try to prove Sarnak's conjecture. And we look into both those things. Proving results about primes kind of went quite well, in that we were able to obtain a version of the twin prime conjecture in this setting, as long as Q is sufficiently large.
Maybe you can just take 1 second and refresh at least my memory as to, I used to know, but why you can only do P squared on twin prime and not P. Where does that come in the proof? I forget.
Okay. I'll get to the proof hopefully sometime later. But it comes from, in very brief terms, we have there's a step of the argument that gives savings, and the savings are proportional in P, but it requires us to accept some loss, because of the Betty number bounds and the loss shrinks with Q, and this is a criterion for the savings to beat the loss. So we need to beat some kind of Betty number bound, and that's where this comes from. So Q has to grow with P, but more significantly, from what I'm about to say, it all has to grow with K. And that's kind of for the same reason the K figures out the Betty number bounds, which means we can't prove a version of Sarnak conjecture. You can state very easily a function field version of Sarnak conjecture by just adapting the definition of deterministic sequence, but you can't. The proof requires Chowla for all K just to prove there's no correlation with a single sequence. And so we can only prove Chowla for finitely many K with any finite field. And we can't prove Sarnak's conjecture for a single sequence with kind of one exception. So there's one class of sequence which you can show no correlation with, given only finitely many autocorrelations in Chowla, which over the integers would be the nil systems, and over finite fields would be generalized polynomials. So if we have the generalized polynomials in this setting are generalized polynomials of degree R in the coefficients of F, and then you could bound that using the UR+1 Gowers norm, for which you need to understand 2 to the R+1 point correlations, which you can do as long as Q is greater than 2 to the R+2 P squared, E squared. Oh, sorry, there's one more. PR. So there's one sequence we can prove Möbius doesn't correlate with, but that's maybe not so exciting because the integer analog of this, Möbius doesn't correlate with nil sequences, was already proven by Green and Tao. And then taking Q slightly larger than this cutoff, we would also be able to show, so we could also show the Möbius function doesn't correlate with generalized polynomials in short intervals. Which is the analog over polynomial in polynomial over finite field setting of the recent work of Matomaki, studying correlations of Möbius with nil systems in short intervals. So the advantage of the function field setting would be for Q large enough with respect to P, we could get shorter intervals than it's possible to get over integers. But it's certainly not as big a gap as for 4-point Chowla correlations, for example. So the situation that we can't get Sarnak's conjecture, despite getting a large finite number of cases of Chowla's conjecture, is kind of disappointing. So that led to thinking about a way kind of around this. Sort of. And that has to do with geometrizing everything. Using a sheaf function as dictionary. So any problem, or most kind of problems in number theory over the integers, we can consider a kind of analog in polynomials or finite fields, which then enables geometry to be applied. But we can go further and try to consider an analog of that problem purely in the setting of geometry. So this was done very successfully with the Langlands program in the setting of geometric Langlands. It was developed first of integers, and it was generalized over to the function field setting, and progress was made at first by Drinfeld using geometric techniques, and then Drinfeld and others realized that those geometric techniques led to kind of purely geometric questions of their own, which have kind of become their own field and found connections with like physics and other areas of mathematics, and then have also gone back and become helpful in the original Langlands program, primarily with the proof of the finite dilemma. And so I don't expect geometrizing Chowla and Sarnak conjecture to be as successful as geometrizing the Langlands correspondence.
It would be pleasant.
But maybe we'll get something interesting, right? If it's 1% as successful, that would already be quite interesting. So how is this going to work? We set a kind of correspondence where on the one side we have a geometric object like a variety, And on the other side, you have an arithmetic object like a set of FQ points. So if you look at the set of monic polynomials of degree n, that would correspond to the affine n-dimensional space, because a monic polynomial of degree n has n coordinates, the line FQ, the n variable coefficients of the polynomial. We think of functions, or really bounded functions, as corresponding to sheaves. We can think of multiplication of functions as corresponding to tensor products. Okay, I should say something about my introduction of sheaves in the talk, which is I will introduce the sheaf theoretic notation, and will try to say things that are still comprehensible if you don't really get what I'm saying about sheaves. And then when we're done with that, depending on how much time is left, I'll say more things that don't depend on sheaves. So please don't like fall asleep entirely if you don't want to hear about this. The Möbius function, which has the starring role in both conjectures, corresponds to a particular sheaf where we take the polynomial discriminant and view that as a function on affine n space, and then build a sheaf, which I'll call L chi, using the square root of the discriminant. We use the double cover defined by adding a square root of the discriminant to define a sheaf. And sums of functions should correspond to sheaf homology with compact support. And bounds for sums should correspond to cohomology vanishing. In high degree. So using this dictionary, we can give a geometric form of Chowla. If we take d1 through dk in F2, instead of summing over polynomial degree n, we'll take cohomology of affine space with coefficients, and instead of a product of functions, we'll take a tensor product of sheaves. And then instead of a bound, we'll do cohomology vanishing for I greater than 2n minus p.
Can you clarify to us, like in terms of dimensions and degrees, where that lies?
Yeah, so this is a sheaf, it's a sheaf that lies in degree 0, times pi is in degree 0. So the kind of geometric analog of the trivial bound, which in algebraic geometry is not entirely trivial, it's a cohomological dimension result of growth indeed, would say this is 0 for I greater than 2n. So just by knowing that this is a variety dimension n, we get the 0 for I greater than 2n, which is analogous to the trivial bound of q to the n. And so we get an additional savings that's linearly proportional to n.
Can you explain why the quadratic character of the discriminant of the irreducible polynomial is -1? Is that what you're basically saying?
Almost. Yeah. So the theorem, which is apparently due to Pillay, is that the Möbius of a monic polynomial is equal to the quadratic character of the discriminant of the polynomial times -1 to the n over 2. No, sorry, -1, that makes sense. -1 to the n. So
Okay.
and then the -1 to the n factor is just totally irrelevant for everything. I'd be happy to explain why that's true. And I can do it now if it would be helpful, or I might do it later. But that's kind of the starting point for the geometric analysis of this problem. And so because we put this statement in its kind of in a geometric home, which is more natural than the method of proof, we don't have restrictions on K compared to the size of the finite field. This suggests it might be possible to prove a geometric version of Sarnak's conjecture using using a geometric version of Chowla. So I can give a kind of reasonable statement of the geometric version of Sarnak. It's unfortunately a bit messy. So we have supposed to given a sequence Fn of sheaves on AN, and we want to show we have.
Is the variable in your sequence?
Yes. So for each n, we have a sheaf Fn on AN. We should have for each k, there exists n such that if n is greater or equal to n, the cohomology in degree 2n minus k of an with coefficients in Fn tensor L chi of delta f should equal 0 if Fn is deterministic. Homology in the sense that for all C, there is like a variety xt So we have to, we're going to restrict this sheaf to short intervals, and short intervals are sets, translates to the set of polynomials degree less than D. So they're D-dimensional affine subspaces within AN. We're restricting it, and we want to say we don't get too many different sheaves. And the way, by restricting, and the way I'm going to say that is I'll have some auxiliary variety, which will parameterize all those sheaves. So a sheaf GD on XD times AD such that for all X and AN minus D, there is Y and XD with F restricted to X times AD. So this is restricting Fn. Restricting the short interval should be isomorphic to GD restricted to Y times AD. So one of the sheaf in our F. So restricting this to any geometric short interval, we should get one of the sheaves lying in our parametric family, GD. So
and in the vanishing section, what's deltas of C?
Oh, delta F. This is the same polynomial discriminant that we've been working for.
Can you give another way, maybe thinking about deterministic here?
I mean, not necessarily. So I mean, this is my attempt to translate as directly as possible the arithmetic definition into a geometric language. What do you not like about this definition? What aspect of it would you like more help thinking about?
Just, I haven't got a feel for it.
Yeah. Okay. Well, I mean, I don't really have a feel for it either. I came up with it, but I don't really.
I mean, one thing about deterministic in dynamics is it's a remarkable thing that the exponential growth is completely decisive in terms of knowing the future from the past. It's a remarkable thing that, like in P equals NP, there's nothing natural about polynomials that I can see. But in the definition of entropy, it was quickly recognized. So there's I don't see an exponential growth.
Yeah, that's correct. And so the reason has to do with, so what's going on here is if you think about how many sheaves can there be on a D-dimensional variety, it's enormous. It's growing at least super exponentially in D, whereas but more importantly, it grows or at least in terms of sheaves that are meaningfully different, give you different functions, it grows meaningfully with Q. The length of this is Q to the D, so the trivial bound would be exponential in Q to the D. And so it's super exponential in Q. And so XD, whatever variety XD is, the number of points is growing. It's exponential. Whatever variety XD is, the number of points is growing polynomially in Q. So as long as you have any kind of geometric variety, no matter how big the dimension of the variety grows with D, it already is saying a really stringent condition on the structure, the structure of your sheaf.
I think that helps.
And so So, and then, okay. So after stating geometric Chowla and geometric Sarnak, we can ask, does geometric Chowla imply geometric Sarnak? And the theorem is that sort of. So geometric Chowla implies geometric Sarnak. Under some kind of independence of L hypothesis. So, which is reasonable if FD arises from Fn arises from geometry. So it should, I think if Fn arises from geometry, it should follow from conjectures on the independence of L of a tau cohomology. So in broad terms, so one of the interesting things about passing to geometry is a lot of things become much easier. In particular, like the bounds we get in this geometric Chowla setting become nicer, but some things become harder. And so like this very simple step in the proof of Sarnak conjecture, you take a number that's large and you multiply it by its complex conjugate and you say it must still be large, is something that's hard to do in the geometric setting unless you make some additional hypothesis or do some argument.
So your sequence of sheaves, Fn,
Yeah.
you're assuming there some weight condition for this vanishing cohomology to have anything to do with estimates?
Yes. So for the vanishing cohomology to have anything to do with estimates, you would need a weight condition. You know, function makes a weight plus 0 is fine. But what you can study the vanishing on its own without the weight condition. But yeah, I mean, so okay. So now is probably a good time to talk about examples.
It's quasi-theorem.
Yeah.
How on earth do you input this independence of L? You get a characteristic polynomial Q and
So,
some.
if your sheaf arises from geometry, it has it has coefficients lying in some field, and there's if you believe independence of L, there should be another sheaf which has a complex conjugate trace function because that's a different embedding of the field, and you should believe those two sheaves behave similarly. That you want those two sheaves to have similar properties and not to have totally different properties, and that is the form that the independence of L takes.
So if you were assuming your F is least in weight 0, then it's linear dual because it's complex conjugate.
Yes, but you don't know that they have similar properties is the tricky thing. So you'd like to know, a simple case of what I'd like to know is you have a least sheaf of weight 0 and it's linear dual, and you look at their cohomology on some variety. If the least sheaf cohomology vanishes in a particular degree, then its dual cohomology should vanish in a particular degree, which if the variety is smooth projective is okay, but if it's not, that seems like a very hard problem. Yeah, that's essentially what's needed. So it's possible to check that statement in certain particular cases, but not in general, I don't think. So part of now would be a great time to give a lot of examples. Unfortunately, I don't really know any very good. I know one good example, but I don't know all the examples. So one nice example is if you take any polynomial Fn on A n, and you form the Argand-Schreier sheaf associated to that polynomial. So we take this cover y to the q minus y is equal to f n, which is a cover with Galois group q. So we get pi 1 of a n, q, and we map that to ql. Click in the group, and that gives us a sheaf. So this sheaf is a geometric version of, well, this is not a generalized polynomial phase, it's an ordinary polynomial phase, or a polynomial, I should say, of degree, some fixed degree d. And this Fn is, deterministic in this sense, because if you restrict it to AD, restrict it to x cross AD, or degree. Okay. Fn is a polynomial of degree k on AD. And so we can let xd be the space parameterizing polynomials of degree k on AD. So I just have to check that a polynomial of k, degree k, in d variables, you can parameterize that by finitely many coefficients. I don't have to check that the number of such coefficients is growing slowly with d. Although, of course. And then in this case, the geometric Sarnak should be true as long as L has even order in the multiplicative group of F. So you get these, in the absence of independence of L results, you can get these kind of weird criteria on L. At least one member of the audience should recognize this condition from my paper with Tim Browning, as also appeared there, and it appears for kind of similar reasons. So the kind of big question I want to raise in this talk is, like, for which dynamical systems have a geometric, algebraic, or canonical nature that suggests that they may have a nice analog in the category, in the setting of sheaves, but don't have Chowla conjecture already known. Okay, I don't have Sarnak conjecture already known. So the question is, like, what are examples of dynamical systems that, for whatever reason, seem like they might translate nicely into the algebraic geometry setting? Just like, clearly polynomial phases translate nicely into algebraic geometry, and even for generalized polynomials, there's sort of something you can do. But unlike generalized polynomials, don't have Sarnak conjecture already a well-known theorem. And if such examples existed, there would be hope to, on the one hand, remove this independence of L hypothesis, at least in that particular case, and on the other hand, maybe introduce some Betty number bounds that convert this into a solution to the actual original Sarnak.
When you comparing with the known cases, either with logarithmic wave or not, let's say not, in no manifolds, you have your analog.
Yeah.
You have the analog of unipotent flows?
I think so, yes, because you can take, so if you raise a unipotent matrix to some integer power, you can express that out with polynomial, the matrix of polynomial entries, and then you can now plug an element of FQ adjoint T into the same formula and get an element in a matrix group over FQ adjoint T, and then you can maybe map that to like a point of Bunge and plug it into a sheaf.
I'd be very interested in that because those are dynamically much more complicated.
But don't we have like strong?
We know is but by a different method, by a method of joining. And only using Raffner, we know that in that case. But without Raffner, we wouldn't know.
Yeah.
In that sense, it's a fundamentally more complicated case than the null manifold, the green power one.
Yeah, kind of very explicit and combinatorial.
So probably make the unipotent sequence also from a function field setting as well, so it kind of lives in that world.
Yeah, I think it's reasonably natural. So the so in the last few minutes, I should say something about the proof of one of these results, and in view of like spending a lot of time saying things about sheaves, let me say something about the proof of the first result, which has key steps that don't involve sheaves. The proof has to do with this key formula that the Möbius of f is -1 to the degree f times the discriminant of f. And this has to do with the thank you, one of the questions that Terry Tao did not get right on his generals exam at Princeton, which is the relationship between the discriminant of a polynomial and the Galois group. Specifically, the Galois acts on the square root of the discriminant by the sign character of Sn.
You should add he was probably 10 years old.
He was a little bit younger than I was when I took my generals. And he and so the Möbius counts the number of irreducible factors, which is equal to the number of so Möbius -1 to the number of irreducibles which is equal to -1 to the number of orbits of the Frobenius map x goes to x to the q on the roots, because each irreducible factor is an orbit of the roots. And -1 to the orbits of a permutation is equal to the sign of the permutation times the number -1 to the to n. And then the sign of the permutation is given by delta square root of delta raised to the power of q over square root of delta, which is equal to delta to the q -1 over 2. And that's the same thing as chi of delta. So it's some kind of elementary calculation using a little bit of Galois theory. We relate the Möbius function, defined arithmetically, to the discriminant, which has an algebraic relation to the actual coefficients of the polynomial and its roots. And the discriminant up to another factor plus or minus 1 that we're going to ignore is the same thing as the resultant of the derivative of the polynomial with the polynomial. So the resultant of two polynomials is the product of the values of one at the roots of the other. And the value of the derivative of a polynomial at the root is the product of the differences of that root with all the other roots. And so we multiply that over all roots, we get the polynomial discriminant. And the resultant of two polynomials is very closely related to another arithmetic object, which is the Legendre symbol or Dirichlet character. So resultant of G and F, if I plug it into this character, I get essentially the Legendre symbol, G over F, which because the resultant by definition is multiplicative. It's a part of the values of G at the roots of F. So it's multiplicative in G and it's multiplicative in F. And then, with some basic checks, you can determine that there's a lot of symbols also multiplicative, and in the case that F is irreducible, you can check that they agree. So what that means, the Möbius function of F, up to some signs that we'll ignore, is the resultant of the derivative of F with F, which at first is not a very useful formula. There's nothing, the derivative of polynomials are complicated, resultants are complicated. It all looks like a mess. Let's flip it over using reciprocity, but there's something very beautiful you can do, which is if you substitute F is equal to R plus S to the P, where R and S are two polynomials, then you get R plus S to the P over the derivative, which is R prime plus P S prime S to the P minus 1. But P is 0, so it's R plus S to the P over R prime, and it's not much effective here. So preserved by writing the Pth powers, you can take a Pth root of R modulo R prime and write R to the Pth root plus S over the derivative. So the Möbius function, when we restrict it to the special set of form R plus S to the P, becomes a shift of a Dirichlet character. And that is very powerful because sums of Möbius function to bound sum over F, the product I Möbius of F plus DI, which is equal to the sum over R and S, the product over I Möbius of R plus S to the P plus DI. It suffices to bound just the sum over S, the product over I, of some Legendre symbol of some constant, some shift of S modulo r prime plus di prime. So modulo the derivative of r plus di. So we turn our Möbius sum into a much tamer arithmetic object, a character sum. The only problem is the character sum is very short. The range of S is like a piece of the size of the range of the original F, but the modulus has size approximately the same size as F, and we have K different modulus. So the length is like Q to the N to the 1 over P, and the modulus is like Q to the N times K. So we get a short character sum like those studied in number theory, but far beyond the range that it can be handled using traditional techniques in number theory. But now we can do a kind of geometric argument. But kind of geometry saves the day at this point. And converting the sum into geometry at this point, one can get a non-trivial cancellation using methods from vanishing sums. Yes, thanks for inviting me to speak.
Yeah, so I have a vague recollection that the Conrad brothers did this strange thing where they fixed a polynomial and then they evaluated it.
Yes,
and it was a violent violation of the parity principle somehow, but you don't get that here.
Yes, so there's it's a funny thing. We're using the same observation. I mean, Mark told me he figured this out independently, and then eventually realized that this R plus S to be trig is the same idea that Conrad and Gross were using, but we're using it in the opposite direction. They were using it to find examples where the parity property.
You should tell him what that example is, and in other words, why you're not contradicting that, right? Is that your question?
Yeah, I mean, I guess it doesn't factor into linear factors.
So their counterexample, you might just point out how it fits into your picture.
Yeah. So their counterexamples is Möbius of any polynomial function in F to the P behaves non-randomly. And it may still cancel depending on F, but it will behave in a non-random periodic way. And so, so a polynomial in F to the P is very unlikely to factor into linear factors, only in the kind of, only in, I guess, some trivial cases, like F to the P minus 1 is equal to F minus 1 to the P, but then the Möbius is just identity 0, and there's no problem. Oh yeah, well, yeah. And so in our second work, we study the polynomial version of Chowla, and we prove cancellation for mu of f, and we prove it in exactly the cases that were not studied by Conrad and Gross. So exactly the cases that are not reversible. And then, but yeah, a product of distinct linear factors is not going to be of that form.
So you still have a bound on the degree of capital F here?
Yes. So if the capital F has degree K, we need Q greater than 4 times K squared, P squared, E squared. So a small loss, which honestly could probably be removed with more work of passing from linear terms to arbitrary polynomials.
All right. Well, let's thank the speaker again.